thank you all for joining. It's gratifying to see so many people come out to hear me talk about something that is really my thing. It'll be more gratifying if most of you return next week. We'll see. I'm going to start a little bit today. Most of the rest of the sessions we'll get right into what we're talking about. Today I'm going to start with a little bit more background for why I'm doing this in the first place, why I think it's worth sharing, what I hope to accomplish a little bit, and then a little bit of background of just some basic concepts of physics that normally I would assume everybody knows, but I'm not assuming anything here. Along those lines, I know there's a lot of people here that don't have a science background, don't have a math background. There will be no math involved here. I'm doing my best
How about a test?
Yeah, the end of the last class, when we talk about relativity, there may be a little bit of multiplication. That's, you know, Einstein relativity, you can't avoid everything. But for the most part, we're going to avoid that to the extent that we can. And I'm trying not to assume any prior knowledge of really anything. So if I start talking about something, or if I say something and it doesn't make sense, or I use some kind of word, raise your hand, ask. I'm more than happy to go back. I want everybody to understand as much as possible. So let me just jump in with why. There's two meanings to this. One is why this class? Why am I doing this? And the other is, and that's also the answer to why I'm doing this class, is the question of why in the first place, right? I came up with the idea for teaching a general interest course like this probably about 5 or 6 years ago, when my oldest son was at that stage as a small child where all the why questions start. Why do we do this? Why do we do that? Why is the sky like this? Why are these lights yellow? All kinds of questions. And what I realized is that I could answer all his questions. And most of the time, most of my answers to his questions were things that I had to use my knowledge in physics to answer, that were not things that people normally knew. And the message there was that there are actually answers to all these questions. So here's just a few. These are just a handful of things that I pulled out from what we're going to talk about today that we'll understand the answers to and understand why. You know, the street lights, the sodium vapor lights, a lot of the street lights are yellow. There's some that are white, but a lot of the time it's yellow and your skin looks funny under it. There's a reason why those are all yellow, why it happens to be that specific color. Fluorescent light bulbs. We all know, you're not supposed to break a fluorescent light bulb. Everybody panics. You're not supposed to throw them in the garbage because they contain mercury. Why do they have to be toxic? Why are all our light bulbs toxic? There's an easy reason for that. Sunlight causes cancer, right? You sit out, you need your sunblock. If you don't wear the sunblock, you don't get your tan. You'll end up with skin cancer. Why does sunlight cause cancer and regular light doesn't? Is there some other light? What's magic about that? What is the actual mechanism that light coming out of the sun would actually somehow create cancer? It's an easy question to answer with some of the stuff we'll talk about today. Some things are magnetic, some things are not. Some metals are not magnetic. What is a magnet in the first place? What is this magic force here? Another thing that, kids with refrigerator magnets, some of them push against each other. Why does all that happen? And then when you get down to technology, electron microscopes, when you see the pictures of viruses or even small bugs or something, it's not a regular microscope. We have to use an electron microscope for that. There's some reason for that. And then technology. We're surrounded by technology. That's one of the things that the kids ask all the time. How do solar cells work? How does glow-in-the-dark stuff work? Why is it not radioactive? Is there any relationship between radioactivity and glowing in the dark? We have DVD players, if we're old enough to have DVD players or CD players, before it was all on the internet. And if it is on the internet, it's all fiber optic now. So what's that? Why is that new? Why did it take till now for everybody to get fiber optics in their house? Whereas where it's based on this stuff. So we'll see what all those things are. But the real message here is not the actual answers to these specific questions. The real message is that there are answers. And that's the magic of physics overall, but it's really why I'm interested in this and why I'm interested in sharing this. Because if I can give you a little bit of an understanding that whenever there's a question, whenever there's something that happens, there is a reason why. And it is possible to understand that reason why. And I think we miss that most of the time going through life, or we just dismiss these things. And that's what attracts people to the subject. And that's what really captures people's interests. So this is a little bit of an outline of where the course is going to go. It doesn't line up exactly with the 6 weeks, but it gives you an idea of where we're starting, where we're going. And there's a spectrum here between a continuum between the useful and the sexy. And sexy is it's a term of art, I guess. It's something people talk about in science all the time, but certainly in physics, some physics is sexier than other physics. A lot of that has to do with how fundamental it is, how close to the beginning of the universe, the smallest possible thing, the most basic forces or anything that you can think of. The more basic, more fundamental it is, the kind of cooler it is, the sexier it is. Also, though, the less practical or useful it is. Once you get to things that are, at energies that we'll never experience, that don't even exist in the universe anymore, and sizes that are so small they're essentially meaningless to anything we do, it's cool, but it's not particularly useful. As we go up from the very small stuff to the bigger stuff, you get where we'll start is with atomic physics, the atom. We'll talk about what an atom is, what it's made out of. The inside of the atom is the nucleus, that core, and that's still fairly useful stuff. With the atom, that's really everything that you experience in your life. Anytime you see something, anything you can touch, taste, technology, and all of chemistry is really just atomic physics a little bit on a bigger scale. So that's where the boundaries of this class, at the top of useful, a little word up here says chemistry. Everything above there is chemistry. And then it gets to biology and other sorts of things. So that's really everything we interact with. And so today's class is not the sexiest, most attractive of the sciences to people who are really into this thing, but it is the most relevant in terms of explaining what goes on in the world. Inside the atom is the nucleus. That's nuclear physics. It's what I did my PhD in, and that'll be mostly what we talk about next week. That really answers the questions of how things came to be the way they are, why we have the materials that we do, why the Earth is made out of the things that it's made out of, why, how stars work, all those kind of big astronomical questions, and a lot of the questions of our origin, not the origin of people, but the origin of the universe as the way it is now. That's really the subject of nuclear physics. And we'll also, you get to see, there's a lot of work done in alchemy over the years, including by some famous old physicists, what Newton spent the second half of his life on. There's a fundamental reason why that could never have worked, and that's because we're talking about, it's a nuclear physics process, not and they're trying to do it with chemistry. So we'll see that next week. If I get a little bit smaller than the nucleus, the picture implies that the nucleus is made up of other things. In fact, it is. And the study of what those things are and what's inside them. And then if you break these things apart and take the parts that are inside, how else can you arrange them to make other new exotic things? That's particle physics. That's where the sexiness really gets into full force there. That's the zoo of particles. There's all kinds of exotic stuff. That's where we talk about gluons. The language gets funny. There's funny, literally funny, as in strange is one particle, charm is a particle, truth and beauty. We talk about glue. We talk about all kinds of kind of silly words that are used to describe it, and color, just as an analogy. And then below where I'm going to get, this is kind of the boundaries of the course. Below that, in the sexier and completely impractical, is where we get to string theory and other things that go beyond string theory, membrane theory, stuff that you hear about a little bit. Mostly those are things that can't be tested, can't be measured. They're good explanations, potentially. They can come up with, if the universe really had 11 dimensions, then it makes all this math a little bit easier and certain things work out. Completely, at least for the foreseeable future of humanity, is not stuff that's going to be directly testable in any way. So that's why it falls below the realm of what's practical. All the stuff that we talk about in particle physics can be tested, can be measured, and to do so, we build special machines in order to do that. So once we go through the basic physics, we'll talk about accelerators and detectors. That's what really is how we know what we know. It's the giant machines that we build. There's Fermilab just outside of Chicago. There's the LHC, the Large Hadron Collider, at a place called CERN underneath Switzerland. The accelerators are the things that make the particles go around fast. Those are the atom smashers. And then once the particles crash, they spit out a whole bunch of stuff. And we look at what comes out. And we have to figure out what's coming out and be able to extract what the physics is from those things. And there's a lot to that. And that's kind of interesting. Within physics, there's a divide between the theorists and the experimentalists. The theorists are the ones who are responsible for figuring all this stuff out. The experimentalists are the ones who actually do it. I was an experimentalist. And so that's where this gets interesting to those of us that want to actually build stuff and see physical objects. And you have to build these giant machines to see these tiny little things. So that's something extreme we'll talk about. That's a picture of a collision. It's one of the ways that we do that. Just a little thumbnail. And then at the end, we'll talk a little bit about quantum mechanics and relativity. Quantum mechanics is the way physics works when things get very small. When things get bigger, it doesn't make any difference to you anymore. You don't see the quantum mechanical effects. You go to what's called classical mechanics, which is billiard balls banging into each other, car crashes, that kind of thing. When you get very small, the rules change, and things happen that are counterintuitive. Things happen that you wouldn't expect to be able to happen. You can start walking through walls. There's all kinds of crazy stuff there. There's also, but those rules, those laws, are the things that govern the behavior of all of this stuff. So occasionally I'll talk about things that happen, and we'll find out exactly why they happen, or more precisely how they happen when we talk about quantum mechanics. That's a huge subject. We won't go into a tremendous amount of detail there, but we'll get enough to understand basically what it's about. And then I group relativity with that. Relativity is different from all the rest of this stuff, except thematically, quantum mechanics deals with things that are very small, the rules get funny. Relativity deals with things that go very fast, and the rules also get funny in a completely different way. The combination of quantum mechanics and relativity is what's responsible for all the physics here that we're going to talk about once you get down to something the size of an atom. Because these little things, it turns out, move very fast. And that those funny rules, those weird things are fun to talk about, even if they're not necessarily that applicable to your daily life. Okay, the conceit for this course is that it's based on, I'm holding this in synagogue, so there's got to be some way I get into the doors here, other than being president. So the idea is that most of the work was done by Jews. Now, I don't know what kind of a coincidence that is, and I'm not really going to spend a lot of time exploring why there's so many Jews that have done this, and why there's so few people that aren't Jewish who have done this. But if you look at the Nobel Prizes that have been awarded for modern physics, there's plenty of Nobel Prizes in physics beyond this. That's also heavily populated with Jews. But about 70% of the Nobel Prizes in modern physics have been awarded to Jews, or there was a Jew in the team that was given the prize. So what I've done here, just as a way to do this, I can share these later if you want. I'm not going to go through all these details. But for each of these topics, these are the Nobel Prizes that were given out. The message here really is there's a lot of them. We start off with Einstein, Bohr, Frank, and Pauli, who we'll be talking about today. There's a half dozen in nuclear physics. There's a whole bunch in nucleons and particles. Again, as you get sexier, the list of things they give Nobel Prizes out for gets bigger. And then even with the accelerators and detectors, and the one thing that there's not much of is in quantum mechanics and relativity. That's not because there's not that many Jews, that's really because there weren't that many prizes given out. Einstein, for example, did not win the Nobel Prize for relativity. There was none given out for relativity, despite the fact that there's two different relativities that we could be talking about. Quantum mechanics, there's a few, despite the fact that it underlies everything we've done, the pieces that went into it get most of those prizes, and there's really just 454 where the prize was given out. So it's not because there's no Jews, it's just because there's not that many prizes there. We like to see pictures of some of these guys sometimes. So these are the four guys that we'll be talking about the work of today. Niels Bohr, who was responsible for the first coherent model of the atom that actually makes sense and explains what you see. James Frank, who we'll talk about what they did later. You'll notice and Einstein here, with most of these guys, these are fairly young pictures. They did their work when they were young. Mostly people in their 20s, or most of these prizes, they were in their 20s, maybe their 30s when they came up with this stuff. Especially the theorists. They tended to be very young when they come up with their good ideas. They do a lot of interesting things afterward, but not a lot of that prize-winning kind of stuff. One example of a picture, though, that's not young is James Frank. He also did his work when he was young, but he did his work in pre-Hitler Germany. His young pictures, he's got the perfect Hitler mustache, and if you look quickly, you might confuse him for a picture of Hitler. He escaped, he worked against the Nazi regime, and was extremely critical of the other scientists that did not leave earlier or did not stand up, particularly the ones that were not Jewish, did not stand up against the regime and did things that in some ways may have at least been silent, if not directly supportive. So I thought that putting a picture of him looking like Hitler would be probably not pleasing to him if he were still around. So I decided to use an older picture, or more recent picture that's not as old. Okay, so this is what we're going to talk about today. There's the why we talk about, what we're going to talk about, we'll talk about. Today's really about atomic physics. Atomic physics, to start with, I'm going to go through some general concepts in physics overall. We'll talk about the cast of characters, who's involved in these things, which particles we have, what an atom is, that's Bohr's Nobel Prize, the different energy levels, decays, think about radioactive decay, that kind of thing, and the lifetimes, how long it takes for something to decay. And then we'll do a little bit on the photoelectric effect, which is what Einstein's Nobel Prize was actually for. A brief foray into chemistry, because that does explain a few things. That's really just an aside. It's a little, chemistry is a tiny subfield of atomic. Quantization, which really underlies a lot of what we're going to be talking about throughout the rest of the course, and that's what the basis of quantum mechanics really is. There's a little quote here, it's so lovely it makes you cry. That's what Einstein said when he saw the experiment that Frank and his partner Hertz performed. So we'd like to get to that. And then that leads to some of the practical stuff that you see in everyday life. And we'll explain what fluorescence is and phosphorescence, how lasers work. Given the fire drill, we'll have to do that quickly. And if we miss anything today, we'll pick it up at the beginning of nuclear physics next week. Okay, so some basic concepts. Charges and forces. Charge. Charge is a basic property of things. So you don't have a charge, you have a particle. And that particle might have a charge or it might not have a charge. So there's two kinds of charges when we talk about electric charge. And that's the negative charge, called flip circle, and a positive charge. Some particles have a positive charge, some have a negative charge, some have no charge. Some, if they get more complicated, could have more than one charge. You can actually have fractional charges. We'll talk later, there's charges of 1/3 and 2/3. We'll worry about in about 2 weeks. What the charges do is they set up a field. So that anytime I have this negative charge, I have some kind of field lines, which are, if you think of a force field, that's really what it is. It's just some kind of more or less invisible magic lines that come out. When another charge comes by, it sees the field lines and then reacts to them in some way, because it has its own field. If I have a negative charge with the field lines going out, and a positive charge, the field lines would go in, these two are going to suck the two particles together. So if I have an electric charge here, with the positive and negative, they get pulled together if they're different. If they're the same, if I have two negative charges, or two positive charges, then the field lines are pointing in the same direction. And they're going to push themselves apart. So with electric charge, the negative charges, two negatives will push apart, two positives will push apart, one of each will pull together. Something else happens with electric charge. If I have a negative charge, or any electric charge, and it's moving, I get a magnetic field. So, oops, getting ahead of myself. If I have a negative charge, and that thing moves, that creates a magnetic field. A moving electric charge is a magnetic field. There is not electricity in magnetism, there is electromagnetism. They are the same thing. Because this negative charge doesn't have to move. It could sit still and I can move. And then it looks to me like that negative charge is moving, and it will have a magnetic field. Okay, so moving charges make a field. Spinning charges, or if something spins, if it moves around in a loop, you'll also get a field. So typically, there's two ways you see magnetic fields come up from moving charges. One is if I have a wire. If I have a wire, there's a bunch of charge that moves through it. That's what we call a current. That's electricity. Anytime I have an electric charge that starts moving, you call that electricity. We put it in a wire just to keep it contained. We don't have to, but that's normally the way we do things. You put the electric charge in the wire, it moves, that makes a magnetic field. That's how you get an electromagnet. If you remember, you wrap the wire around a nail, the electric charges move through, you get a magnetic field, and then I can do something magnetic. We'll talk in a little while about what magnetism is. So that's the other thing that happens, though, not just in a wire. Yep.
So, just, I don't know if you want to get too complicated, but just on that premise, on that basis, so what creates the negative charge to begin with? And the other thing they used to tell us in school that always amazed me was you move the wire through a magnetic field and a current appears in the wire.
Right. Okay.
It's all magic.
Sure. So where the charge comes from is a little bit easier because it just is. It's which I hate to say, and you know, when we get down to the real particle physics stuff, we'll see there's certain things you can explain everything in terms of other things, but you have to start with something. And some of the things that we start with, charge is one of them. We were really trying to figure out how mass didn't have to be one of them, and that's what the discovery of the Higgs boson was all about. But there's a handful of basic properties that you need and a handful of basic particles. There are 12 basic particles. There are a couple of different properties, and those are just things that we start with. So there's no way to, you get to a certain irreducible size. That's really the point of all this, is to get to what is that fundamental beginning thing. Maybe in 100 years somebody will figure out how to connect the emergence of charge with the emergence of some of the other properties. Now, the other piece, though, that is a good point. If I have a moving charge, that makes a magnetic field. If I have a magnetic field, so a moving charge is a current, there's electricity, it gives you the magnetic field. If I have a magnetic field and I move something, and I have a charge, that'll make the charge move as well. So if I have a changing magnetic field, that will make charges move. So the magnetism and electricity kind of trade back and forth like that. It's a symmetric relationship. If you take a look from the perspective of the magnetic field, or just turn around and look from the perspective of the electron, you'll see of the charge. You'll see that they're the same thing. They trade back and forth like that. A moving charge makes field. Moving field will cause the charge to move. Okay, so that gets us through the moving charges field. Conservation laws. It's actually your other question here. There are certain things that are conserved. We have conservation of matter, conservation of energy. The first one is the conservation of energy and matter as one thing. I can change from matter to energy. I can change from energy back to matter. That's the E equals mc squared idea. It doesn't really matter. From a basic physics perspective, energy and matter really aren't distinct things. They're just different expressions of energy. It's all just energy. Okay, so that's, but that total of energy and matter together, I have to keep. I can't destroy it. So if I have energy, that can turn into matter. If I have matter, I can turn into energy. I can trade mass for something moving faster, but I can't get rid of that total. That's always going to be exactly the same from the beginning of the universe till now. So when the universe was created, however much energy it had, that's how much energy we have today. That's how much we'll have at the end when the universe collapses or destroys or whatever it happens to do. Might get spread out more, but that total amount of energy will always be the same. The other thing that's important that does not get created or destroyed is charge. So if I have a certain amount of charge, certain number of charges, I can't do anything about that. They are always going to be there from the beginning to the end. I can combine them, I can take a positive and negative and put them right next to each other, and then they'll look like they'll cancel out. So if I have a plus and a minus together over here, and I stand over here, it'll look like 0 to me. So I won't see the charge, but it's still in there. If I break that thing apart, those charges will come apart, and I'll be able to see them separately. Spin, or angular momentum, is the other thing. If I have something moving around, it has momentum. And that angular momentum, that spinning idea, and there's two kinds. One is if I'm moving around in a circle like this, I'm on a merry-go-round. I have a certain amount of momentum. That's the force that continues to keep it moving. So if I spin a merry-go-round, it keeps spinning on its own. And if I reach my hand into it, it's going to hit me hard, right? That's that momentum there from spinning around, this angular momentum. And the amount of that is always the same at the beginning and at the end of whatever we do. That comes up a lot when you're taking like freshman basic physics with the billiard balls. That's still true there. What's different when we get down to this kind of particle physics stuff is there's a different kind of angular momentum, which is officially called intrinsic angular momentum. We call it spin. That's just the normal name that's used, unless you're speaking in French, in which case they don't like spin and it's momentum angular intrinsique. But that's the way they do it. It takes a long time to read those papers. But the spin behaves exactly like the angular momentum from something going around on a merry-go-round, and you can actually trade back and forth between those two kinds of angular momentum. But there's nothing that's actually spinning in those cases. We just have something called spin. And usually spin is in fractions. An electron, for example, has the spin of 1/2. And we add the spins together, and the spins, the way we talk about spin also is in terms of spin up or spin down. So I have this electron, and you can just think of it as spinning. It's not actually spinning. It just behaves as though it is spinning. There's actually no it to spin. And it can spin this way, in which case we call that spin up, because if you take your hands and curl them around, the way it's spinning, your thumb points up. So that's spin up. And if I'm spinning the other way, then I curl my hands this way, that's spin down. So generally, if I have something that's got spin 1/2, it can be spin 1/2 up or spin 1/2 down. And the funny thing about spin is when you look at it in a mirror, because there's certain physical properties where you're actually looking at a reflection. That's what antiparticles turn out to be, we'll talk about in a couple weeks. If I look at most things in a mirror, if I look at charge in a mirror, if I have a negative over here, look at it in the mirror, it's still negative, nothing changes. If I have something that's spinning this way, if you go home and turn your head in the mirror, you'll see, if you turn this way, and you look at your image in the mirror, it's turning the other way. So if I have something that's spin up, when I take the reflection of that, it'll actually be spin down. So spin flips when you do that mirror reversal on that. So there's a few other things, but that we'll talk about as time goes on.
Sir,
Yes?
how can spin be less than 1? Is it a normalized index of something?
Is
it normalized with reference to something, or is it an absolute term?
It's an arbitrary absolute thing. It makes it easier to, the reason is that we define things as spin 1 that are the usual observable stuff. And so when we have smaller components, if we make them fractional, they tend to add up to 1 when we're talking about something that's big enough that we interact with. So all these numbers, all these values are essentially arbitrary. They're just done to make the arithmetic, the mental arithmetic, a little bit quicker.
And its significance is in terms of matter and movement, where it's really a product of matter by velocity?
No, it's not actually a product of the movement, of the velocity of the matter. It's just an intrinsic property. It's like charge. It just is, in a sense. What happens with spin, though, is that you can, in that conservation of angular momentum, you can convert from the spin to the physical movement angular momentum, and that's what has to be preserved. The actual spins themselves don't necessarily have to be preserved. But it's just an intrinsic thing that just appears, was born with the universe. Okay, next one is the wave-particle duality. There's a lot written about it. There's a lot we'll talk about. When we get to quantum mechanics, that's a big thing. There's a whole lot of experiments that show you how it works. It's not all that interesting to us for what we're going to talk about now. What's the way to understand it? And this is one of those cases, and I'm going to try to point out cases when I'm lying to you. Sometimes I'll forget. But this is one of those cases where I'm going to lie to you, but it's going to give you the right impression, so that as we talk about things, you'll understand what's going on. The idea is that every particle is also a wave. And sometimes you look at it a certain way, it looks like it's behaving like a wave, and if you look at it other times, it looks like it's a particle. So a wave, for example, isn't any place. A wave is a wave. Where's that wave? There is no where's that wave. If I have a particle, the particle's right there. But these things both kind of coexist in everything all the time. There's a relationship which is just based on the amount of energy the thing has as to what its wavelength is. So the wavelength is how tightly spaced these wave lines are. So I can have a small wavelength, which is like this, or I can have medium wavelength, I can have a really long wavelength like that. And that's just related to how much energy there is in the thing. The more mass it has, the...
Just a quick question on that.
Sure.
I've always heard this discussion only with regard to light.
Yes.
So, but you're defining it generally.
Right, so light started out, the idea of light originally was that it was a wave. And everybody thought it was a wave, and it behaves like a wave for everything anybody ever did until about 1906 or 7, something like that. Light was just a wave. And everything else was a particle. But it turns out that light is actually carried by particles, and any particle is also a wave. Now the particle does not actually move like a wave. But for our purposes for the next 6 weeks, you can believe it does. You will get the right idea if you think of, okay, I've got my particle doesn't just fly, my particle wiggles around as it flies.